Welcome to this exciting journey into the world of traffic sign recognition using computer vision. In today's fast-paced world, autonomous vehicles and driver assistance systems are rapidly becoming the future of transportation. A critical component of these systems is the ability to recognize and interpret traffic signs accurately and in real time. This project harnesses the power of deep learning and computer vision to automatically identify traffic signs from images or video input. By using convolutional neural networks, commonly known as CNNs, we're able to train our model on thousands of traffic sign images, enabling it to learn complex patterns and distinguish between different types of signs such as stop, yield, speed limit, and pedestrian crossings. The German Traffic Sign Recognition Benchmark, or GTSRB, is used as our primary dataset. It contains over 50,000 images categorized into 43 different traffic sign classes. After pre-processing the data, resizing, normalizing, and one-hot encoding labels, we build and train a CNN using TensorFlow and Keras. Once trained, the model achieves high accuracy on both training and validation sets. To evaluate real-world performance, we test it on unseen images, ensuring it generalizes well. The applications of this project extend beyond just cars. Smart city infrastructure, road safety systems, and traffic enforcement tools can all benefit from accurate and real-time traffic sign detection. In conclusion, traffic sign recognition using computer vision is a critical step toward building safer and smarter transportation systems. With advancements in AI and deep learning, the dream of truly intelligent roadways is well within our reach. Let's begin by preparing our workspace. In this step, we install essential libraries like Datasets to load traffic sign images from Hugging Face, and torchvision for image transformations. These tools are the backbone of our image preprocessing and deep learning pipeline. Here, we import everything we need: NumPy for numerical operations, Matplotlib for visualization, Hugging Face's datasets, and PyTorch libraries to build and train our convolutional neural network. These imports set the stage for the entire recognition system. We now fetch the GTSRB dataset from Hugging Face. Specifically, we're using the tanganke/GTSRB version, which includes clear traffic sign images labeled into 43 different classes. We load the training split for model development. In this step, we define a set of image transformations. Each traffic sign image is resized to 32 by 32 pixels, converted into a tensor, and normalized. These operations ensure that the input format is consistent and optimized for neural network learning. Next, we create a custom PyTorch dataset class to wrap around the Hugging Face dataset. This class applies our transformations to each image and makes the dataset compatible with PyTorch's data loader for efficient training. We divide the dataset into two parts, 80% for training and 20% for validation. This separation allows us to train the model on one portion and test its performance on unseen data, helping us identify overfitting or underfitting. Here we define our convolutional neural network. It has two convolutional layers followed by pooling layers to extract and downsample features, and two fully connected layers to interpret those features and output class probabilities. Dropout is included to prevent overfitting. The loss function we use is cross-entropy loss, ideal for multi-class classification. The optimizer is Atom, a popular choice that adapts the learning rate for faster and more stable convergence. Now we train the model over multiple epochs. During each epoch, the model processes every batch of training data, updates its internal parameters through backpropagation, and minimizes the classification error. Training progress is printed after every cycle. With training complete, we switch the model to evaluation mode and test it on the validation dataset. We calculate the total number of correctly predicted traffic signs and derive the overall validation accuracy. This shows us how well the model generalizes. In this step, we save the trained model to a file. This allows us to reuse the model later for inference, testing, or even deploying it in a real-time traffic sign recognition system without retraining. We reload the saved model into memory. This is useful when testing the system later or deploying it in another application. We also ensure the model is in evaluation mode to disable any training-specific behaviors like dropout. To demonstrate inference, we take a single image from the dataset, apply the same transformations, and feed it into the model. The model predicts the traffic sign class, which we then compare to the actual label and display the image along with the result. Finally, we test the model on the official test set provided in the dataset. This gives us a final, unbiased measurement of how accurate our system is. The result tells us how reliable the model is when deployed in the real world.